Let's do system design for search systems. Today we'll dive into the fascinating world of search systems and how they enable users to find relevant information efficiently. We'll be taking example of x.com or Twitter in this course. So whether you are searching for tweets using keywords, hashtags or usernames, a well-designed search system ensures fast and accurate results. As we know, the first step in doing a system design is its functional requirements. So let's just write those down. The first requirement is that the users can search by keywords, hashtags or username. So imagine a user is trying to find tweets related to a specific topic or person. Our system allows users to input keywords, hashtags or usernames, and in return, it displays all the related tweets. The results are shown from newest to the oldest, ensuring users always get the latest information at the top. The second requirement is the fuzzy search. Users will be able to do fuzzy search for mistyped queries. Have you ever typed something wrong but still expected to find the right results? Well, that is called fuzzy search. This is where fuzzy search shines. For instance, a user might mistakenly type quantum computing. That is, there is a spelling mistake at O. It should have been quantum computing. Despite the typo, our system should still return relevant tweets about quantum computing. This forgiving nature is very critical for search system. This makes it user-friendly, where small mistakes don't prevent users from finding what they need. Now, why all of this matters? An efficient search system is more than just about finding the exact matches. It's about enriching the user experience, making search results relevant, timely, and intuitive. By incorporating features like fuzzy search, we ensure that errors are forgiven, users don't need to worry about minor typos, search is fast, results are shown quickly, helping users find what they need without frustration, and thirdly, content is relevant. So whether it's a keyword, hashtag, or username, the system delivers accurate results, saving users time and effort. Search systems are one of the most critical components in modern platforms, and their design can make or break the user experience.
Before diving into the actual architecture and design of any system, we must first consider the non-functional requirements, also known as the NFRs. These are the qualities or attributes of the system that determine how it performs rather than what it does. In essence, while functional requirements define what the system should do, example search for keywords or hashtags, NFRs set the bar for how well the system performs those tasks. NFRs are crucial because they influence the system's scalability, reliability, speed, and user experience. If we only focus on the functionality and completely ignore these NFRs, we might build a system that works initially, like your side project or weekend project, but struggles under the load, or it even fails to provide smooth experience for users as it grows. So for our search system, these would be our key non-functional requirements. The first one, availability. So what does availability mean? Our system should be available 99.9999% of the time, that is 6 nines. This ensures that users can always perform searches even during the peak loads or minor system outages. Now, why does it matter for the search system? In search systems, users expect instant results, regardless of how many people are using the platform at the same time. With millions of users searching simultaneously, it's critical that the search function remains highly available to everybody. So for example, imagine Twitter's search going down during a major event like the Olympics. Users would be frustrated and the platform could lose significant engagement. To prevent this, we need to ensure that our system is highly available. And we can do so by techniques like server redundancy and failover mechanisms. We don't need to dive too much deep into that, but that's the overall feel for this one. The second one is the low latency. So what it means is that search results should load quickly. Any noticeable delay, even a few seconds, could frustrate users and lead to a very negative experience. It's a very bad experience if the user has to wait a lot. Users are accustomed to instant feedback, whether searching for breaking news or trending hashtags. Waiting too long for results can lead to frustration and even cause users to leave our platform. So we do not want that. Let's say a user searches for hashtag World Cup 2024 to stay updated with the live match scores. If the search takes more than a second or two, users may abandon the search and then look for updates somewhere else, some other platform. Maintaining low latency ensures the system keeps up with the user expectations and keep them engaged with our platform. The third one is scalability. Our system must be able to handle a good growth. As the user base of the platform expands, the search system should be able to scale seamlessly, ensuring consistent performance. As our platform grows, more users perform more searches, often simultaneously, that is at the same time. A well-designed search system should scale with the platform, ensuring that it can handle increased load without any degradation in performance. So let's say our Twitter search platform currently handles 10 million users, but in the next year, it is projected to handle 50 million users. So if the search system isn't scalable, it will likely buckle under the increased load, resulting in downtime and slower response time. Building scalability into the system from the start ensures that we do not land up in that situation. So in conclusion, non-functional requirements like availability, latency, and scalability are critical to our search system. It ensures that our system works efficiently and provides a seamless experience for users. Addressing these early in the design process allows the system to handle real-world demands and remain robust as the platform grows.
So before building any system, capacity estimation is crucial. It helps forecast the resources your system will need in order to handle anticipated user traffic. It ensures that your system remains reliable and scalable. So without it, your system might crash under real-world usage or waste resources by over-provisioning. For our search system, capacity planning ensures that millions of users can search content seamlessly every day. There are two key metrics for our user load. These are some reasonable metrics that we assume beforehand. The first one is daily active users. Daily active users is the number of unique users engaging with the system in a day. And the second one is monthly active users. As the name suggests, it's the number of unique users interacting with the system over a month. Now, why are these metrics so important? Daily active user helps estimate the peak load of your system faces on a given day. And monthly active user provides a broader perspective on long-term user activity and growth, helping plan for future scaling needs. So for our search system, we will assume that our daily active users are somewhere around 100 million and monthly active users 400 million. This means 100 million users will be actively searching daily, giving a clear picture of the daily traffic load. 400 million users monthly implies you need infrastructure capable of handling consistent, sustained traffic throughout the month. These numbers are key for determining system scalability, ensuring it can manage high usage and peak events without downtime. So in summary, daily active users and monthly active user are the foundation of capacity planning, and with 100 million daily active users and 400 million monthly active users, your system search requires careful infrastructure planning to maintain high availability and performance. After estimating daily active users and monthly active user, the next step in capacity planning is the throughput estimation. Throughput measures how much data the system needs to process over time and is crucial to ensure the system can handle user requests without performance degradation. It helps us plan for the expected load and avoid system bottlenecks. There are mainly two types of throughput when we talk about it: the read throughput and the write throughput. Read throughput, as the name suggests, this measures how much data is being read from our system, such as fetching posts, loading user profiles, or searching for information. That is, we are trying to read from our system. Users are trying to read from our system. And the second one is the write throughput. This refers to how much data is written or inserted into our system, like creating posts, saving settings, or even uploading content. We are pushing to the system, we are writing to the system. Both types are important when building a balanced system, but they depend on the functionality being considered. In the case of search functionality like Twitter, we are primarily concerned with the read throughput, as the system reads data based on user searches. So let's say a user tries to search for something, they are trying to read from our system. So let's calculate the read throughput for search operations. Let's assume each user performs 5 searches per day. So daily searches would be daily active users into 5. That is 500 million searches per day. To understand how many searches happen every second, we'll simply divide this number by 24 into 60 into 60. Why so? Because that would give us 500 million searches divided by 24, that is for 24 hours, 60 for 60 minutes, and then 60 for 60 seconds. So 500 million divided by 24 into 60 into 60, that gives us 5787 searches per second. So our read throughput comes somewhere around 5700 searches per second. This number helps us understand the real-time load of the system. It's essential to ensure that the system can process this much load while maintaining low latency and high availability. When designing a search system for Twitter, the big question is, what data are we searching though? The answer is tweets, and more tweets. So it's time to figure out just how much space we'll need to store all that data. But before that, we need to ask ourselves a question. Why do we even need to estimate the storage? Imagine your system running out of storage space. Without proper storage planning, the system could slow down or even lose data as it tries to handle more and more tweets. And in a world where millions of users are constantly tweeting, storage is key to keeping things running smoothly. So what's the goal? To make sure we have enough space to store all the tweets while keeping the system fast and reliable. So let's go on with our storage estimation. Our search system is all about handling tweet text. So here's what we need to know. As we already know, daily active users is somewhere around 100 million. Now we'll make an assumption here. Each user tweets on average once per day. And another assumption would be average tweet size. Let's say the average tweet size is 200 characters per tweet. That is somewhere around 200 bytes. Now using those assumptions, we would calculate how much storage we need every day. So total storage per day would be 100 million users into 1 tweet per day into 200 bytes per tweet. 100 million for the daily active users, 1 tweet per day, that is the frequency for each user, 200 bytes per tweet is the size of a tweet. Now if you multiply all of this, the result comes out to be 20 billion bytes per day, that is 20 GBs per day. But wait, let's not just plan for one day. We need to think long term. What happens in 10 years down the line? So total storage in 10 years would be 20 GB per day into 365 days into 10. That comes out to be somewhere around 73 terabytes. Now why this estimation matters? So with 73 terabytes of data over 10 years, we are talking about a massive amount of information. And guess what? Your system needs to be ready to store all of it without breaking a sweat. So in short, when it comes to storage, we are planning for the long haul. By estimating the storage needs upfront, we are making sure the system has the capacity to store millions of tweets, keeping the search functionality lightning fast and ready for the future. Now imagine you are running a search system like Twitter. and millions of users are searching for the latest tweets. Now, would you want to wait around while your system pulls data directly from the database for every single search? Of course not. That's pretty slow. That's where cache memory comes into the picture. So, why cache is your secret weapon? Accessing data from a database is like waiting in a long line at the coffee shop. It takes a lot of time. But with cache, it's like having your favorite drink already waiting at the counter. Cache stores frequently accessed data, allowing users to get what they need faster and lightening the load on your database. If you talk about the search system, in a search system, caching helps with three things. The first one, speeding up search results for the most popular data. Secondly, reducing stress on the database. And thirdly, deliver a smooth experience to the users. All three are very important, and that is why you see cache being used more often nowadays. Now let's crunch some numbers. Here's the fun part. Let's estimate how much memory you'll need to cache those high demand tweets. We already estimated the total storage of tweets per day as 20 GB. Now let's assume we want to cache 5% of the most frequently accessed data. Why? Because these are the ones people search over and over again. So we'll take 5% of 20 GB. So that would be 1 GB per day of cache memory. This means to keep things fast and responsive, we'll need 1 GB of cache memory per day to store those top tweets. Now, one thing to note here, as the system grows, so does the amount of popular data as well. We can't just set and forget the cache size. As your user base expands and more tweets get generated, we need to make sure the cache grows with it. The system should be able to scale. So we are always caching the hottest data and keeping users happy with blazing fast search results. Now, when we design a system, it's not just about storage and processing power. We need to also think about how much data flows into our system and out of our system per second. That's where network or bandwidth estimation comes in. It tells us how much data flows in and out of our system. Data flowing in per second is also known as ingress, and data flowing out per second is also known as egress. So are you ready? Let's dive into the data stream. First up, let's figure out how much data is flowing into our system. This is all about the tweets being generated and saved. Now, we know that the data being stored per day is 20 GBs as per our storage estimation. So the amount of incoming data per day is 20 GB per day. Now let's break it down to how much data flows in per second. It is very easy to calculate this one. You simply need to divide 20 GBs by 24 into 60 into 60. Why so? Well, 24 into 60 into 60 is for 24 hours, 60 minutes and 60 seconds. So we'll simply divide 20 GB data coming in a day divided by 24 into 60 into 60. That comes out to be 231 MBs per second. So that's 231 MB of fresh tweet data pouring into the system every single second. Now, very similarly, let's move on to the egress calculation. That is how much data flows out of our system. Now, egress is all about data being searched and returned to the users because that is the data that flows out of our system. Now, as per our throughput estimation, we are handling somewhere around 500 million search requests per day. And each search, let's say, returns 10 tweets. And we already know that each tweet is somewhere around 200 bytes. So that gives us outgoing data per day, which is equal to 500 million requests into 10 tweets into 200 bytes. That gives us 1000 GBs per day, which is 1 TB a day. Well, if you imagine, that's a massive amount of data flying out to the users. Now let's figure out how much data flows out of our system per second. Now, similar to our calculation to ingress, we'll simply divide 1 TB by 24 into 60 into 60, which is equal to 11.5 GBs per second. That's 11.5 GBs per second of tweet data being read and sent back to users through the search results. Isn't that a huge amount per second? Now, why bandwidth matters? These numbers are no joke. With 231 MBs per second flowing into the system and 11.5 GB per second flying out of our system, your network bandwidth needs to be ready to handle these massive data flows. Without proper bandwidth planning, the system could slow down, or even worse would be to see users could experience a lot of lag during searches. And nobody wants that, right? So in summary, network or bandwidth estimation is all about understanding the data flow in and out of our system. With 231 MBs per second of incoming data and 11.5 GBs per second outgoing data, your system needs to be equipped to manage this flow efficiently and keep everything running smoothly. Let's move on to the API design section. We'll do API design for our search functionality. So what happens when you hit search? Take a look at John, our user. He's super curious about quantum computing. So he opens Twitter, types quantum computing in the search bar and hits that search button. But what happens next? Let's break it down. First, we need to ask what's the action here. That would give us the HTTP method. So when John hits search, we need to tell Twitter's server what action to perform. Since we want to retrieve a list of tweets, we use the get method. It's like telling Twitter, hey, give me all the tweets related to this search. So that is why the HTTP method here is get. The second question we need to ask is where's the action happening? That is the endpoint. Now, John's request needs to go somewhere on Twitter's server. This somewhere is called an endpoint. In this case, John's search will hit the /v1/search endpoint. But wait, how does the server know what to search for? Simple. We pass the search keyword quantum computing using query parameters. So our endpoint looks something like this. /v1/search query equals quantum %20 computing. Note that we do not have a space then but %20 in the URL. Let's decode that mystery. So why didn't we just write quantum computing with a space between the words? Well, spaces in URLs can be confusing. The servers might think the URL ends at quantum, ignoring the computing part entirely. To prevent that confusion, we use something called as URL encoding. The space is replaced by %20, ensuring that the server processes the entire query. Pretty smart, right? And on the back end, Twitter server decodes %20 back to space. So it knows John is searching for quantum computing and not quantum %20 computing. So in summary, we know that the HTTP method is get and the endpoint as /v1/search query equals quantum %20 compute. Now, John's request has reached Twitter servers. Now the magic is happening there. Twitter servers dig into their database, find tweets mentioning quantum computing and package them up in a nice, neat JSON format. John will get a list of tweets, each with important details like tweet, text, user, and time posted. Here's an example of what John might receive. The JSON would look like this: tweets and then a list of tweets. And in each of the brackets you see, these are the different tweets. So one of the tweets is saying exploring quantum computing, while the other is saying revolutionizing fields with quantum computing #. So after all of this, John can see a list of tweets mentioning quantum computing on his screen. Let's now move on to the high-level design. We'll do the high-level design for our search functionality. So let's walk through a basic search flow on Twitter, focusing on how it works. Meet John. He's curious about quantum computing and goes to Twitter or x.com to search for it. Here's what happens next. Step 1. John types quantum computing into the search bar and hits enter. His search request gets sent to Twitter's API gateway. The API gateway is like the gatekeeper. It checks the request, makes sure everything is okay, and prepares to send it forward. Now in step 2, after validating the request, the API gateway sends it to the search service. But before it reaches the search service, it passes through a load balancer. The load balancer ensures that the request is sent to the least busy search service server. As you all know, there are multiple servers for this search service, so load balancer ensures that the request is sent to the least busy one. It balances the load. Step 3. Once the request hits the search service, things get a little tricky. The search service looks at John's query, picks out keywords, in this case quantum and computing, and gets to work. But here's the problem. The system isn't smart enough to narrow down the search quickly. Instead, it starts scanning the entire tweets database, looking for any tweet that matches those keywords. If you want to imagine how slow that is, imagine trying to find a specific book in a library without any catalog or index. You'd have to search through every single book to find the right one. That's exactly what the system is doing here, scanning the whole database for every search. Well, this works, but as the system grows, it starts to slow down. Step 4. After scanning the database, the system finds tweets that contain both quantum and computing. These tweets are then sent back to John as search results. John gets this result, but this approach is very far from ideal as we have seen. As the number of tweets and users grows, this method will start to drag. You might have guessed it, like this approach definitely works, but it's far from optimized. Scanning the whole tweets database for every single search will become painfully slow as the system grows, especially when we are talking about a system like Twitter or X.com. It's clear that this design can't handle high volumes of queries efficiently. Time to optimize this in the next one. Let's move on to optimize our high-level design. We'll use indexing for our search functionality. Previously, we saw that scanning the entire database for keywords was painfully slow and inefficient. But what if we had a magic list that instantly gave us the tweets containing our search keywords without all that scanning? Well, guess what? This magic list exists, and it's called the IndexedDB. So imagine John searches for quantum computing on Twitter. Instead of hunting through every single tweet, the IndexedDB swoops in and instantly gives us all the tweet IDs that contain quantum and computing. No need to check every single tweet. This is the power of indexing. So let's break down how this optimized search flow works step by step. So step 1 remains the same when John types quantum computing and hits search. His request is sent to API gateway just like before. The API gateway checks and validates his request before moving forward. Step 2. Once validated, the API gateway sends the search request to search service via a load balancer. The load balancer makes sure the request reaches the least busiest search service server. Now we move on to step number 3. Here's where things get really fast. The search service picks up the keywords from John's query, quantum and computing, but instead of scanning the entire tweets database, it checks the index database. This is where the magic happens. The index database tells the server that quantum appears in tweets 1001, 1002, 1003 and 1005, and computing appears in tweets 1002, 1003 and 1005. Now the search service doesn't need to check all the tweets. It simply takes the intersection of these two lists, which is 1002, 1003 and 1005, the tweets that contain both these words, quantum and computing. Step number 4. With the tweet IDs in hand, 1002, 1003, 1005, the search service now retrieves the actual tweets from the tweets database. No more scanning through everything. Step number 5. Finally, the search service sends these specific tweets back to John as a search results. Now, why indexing rocks? Thanks to the index database, we are no longer scanning the entire database. We can quickly and efficiently find the tweets containing the keywords and return the results in a fraction of the time. It's like having a supercharged search engine under the hood, making sure the system scales smoothly even with millions of users. Now, until now, we have done high-level design for our search functionality, but there are slight changes that we need to do here. We all make mistakes, right? Whether it's a quick typo or misspelling. It happens, right? But when you are on Twitter, you have probably noticed that even when you type something wrong, you still get the right results. That's the magic of fuzzy search. Fuzzy means unclear or ambiguous, and this technique allows the system to correct your typos on the fly. Let's take John, for example. He accidentally searches for quantum computing. You see the misspelling there? T-O-M instead of T-U-M. So our Twitter search system still delivers the right results. Let's walk through how this happens. Step 1. John types quantum computing with the misspelling into the search bar. As soon as he hits search, his request is sent to the API gateway, which validates the request to make sure everything is in order, right? And then comes the step number 2. Once validated, API gateway sends the request to the search service via a load balancer. The load balancer ensures that the load is distributed among all the servers in the search service. Third step, checking the index database. Here's where things start to differ. The search service picks up keywords quantum and computing from John's query. It then searches the index database to see if these keywords exist. There's no such thing as quantum in the index database. What now? Well, in step number 4, the search service realizes that quantum doesn't exist, so it calls query correction service. Think of this as spell checker of search queries. The query correction service takes quantum as input and guesses the most likely correct word. In this case, it's quantum. Well, a fun fact here. This correction happens behind the scenes with algorithm designed to understand common typos and misspelling, which we'll cover in the deep dive insights. Step number 5. Now that the correct keyword is found, the search service runs a new search in the index database with quantum and computing. The index database quickly returns the tweets containing both keywords, very similar to the way we have seen earlier. Quantum appears in tweets like 1001, 1002, 1003 and 1005, whereas computing appears in tweets like 1002, 1003 and 1005. As we have seen, we take intersection of both these lists and we can find tweets 1002, 1003 and 1005 which contain both these words. Step number 6. With the correct tweet IDs 1002, 1003, 1005 in hand, the search service fetches the actual tweets from the tweets database. And step number 7, finally the corrected results are sent back to John. Even though he misspelled quantum, the system smartly corrected it to quantum and delivered the right results, saving John from frustration. Here, as you can see, by integrating a query correction service, we keep the search process smooth and intelligent, handling millions of searches without breaking a sweat, even if people make typos and misspellings along the way. So until now, we have seen high-level design for our search functionality, where we have seen the indexing part and we have also seen how to support the fuzzy search functionality. So now let's move on to the ranking part. So let's say John searches for quantum computing on Twitter and boom, the most relevant tweet magically appears at the top of the list. But there's no magic here. It's all thanks to our ranking service. So ever wondered how Twitter decides which tweets to show first and which tweets to show later on? Well, the ranking service is like the sorting hat of Hogwarts. It makes sure that the relevant and important tweets appear first. So let's break down how John's searches gets from chaos to perfectly ordered results in just seconds. So most of the steps here are very similar to what we have seen until now. So in step 1, John types quantum computing, oops, there's a typo there, and hits search button. So the request zips over to the API gateway where it checks to make sure that everything looks good. Well, there's a fun fact about API gateways. API gateways are like the bouncers of the internet. They let the right requests in and keep the bad ones out, ensuring security and performance. Step number 2, the API gateway sends John's request to the search service via the load balancer, which is very similar to what we have seen until now. Step number 3, the search service picks up the keyword quantum and computing from John's search. It checks the index DB for these words. There's no quantum. The word quantum is missing. So here's when our step number 4 kicks in. The query correction service sweeps in to save our day. It recognizes quantum as a typo and fixes it to quantum. The system is smart like that. It's just like an autocorrect system. Another fun fact, did you know that query correction uses algorithms very similar to our spell checkers? These algorithms are trained to recognize common typos and fix them in real time. Now moving on to our step number 5. Now that we have got the correct keywords, quantum and computing, the search service checks the index database again and finds out the tweet IDs where quantum and computing are there. Step number 6. The search service then fetches these tweets from the tweets DB. It's almost ready to deliver the results to John, but wait, we need to make sure the most relevant tweets come first. So that's the part of ranking, which is the step number 7. Here's where the ranking service works its magic. Before showing the results, the search service hands off the tweets to the ranking service. It sorts them based on the relevance, in this case it's newest to the oldest. But one thing to notice here, here's the genius part. By having a separate ranking service, we can easily change how we rank tweets later on. Whether we want to rank by likes, tweets or relevance, we only need to update this one service. It's called decoupling and it's the key to flexible future-proof software. Something to learn in our designs. Another fun fact here. Want to know how ranking gets even smarter? In some systems, ranking algorithms take into account personalization. Meaning if John loves reading about cybersecurity, tweets about that might show up higher for him. Isn't that interesting? Now we move on to step number 8, where results are given back to John. So finally, the ranking service gives the sorted tweets back to the search service, which then sends them back to John. He now sees the most relevant tweets perfectly sorted from the newest to the oldest, and all of this happens in just milliseconds. Now, what would have happened if we didn't have this ranking service? So without the ranking service, John might see outdated or irrelevant tweets first, maybe an year ago, 2 years ago. But thanks to this clever design, the results are sorted, relevant and easy to update as search trends change. And because the ranking service is separate, it's super easy to tweak the ranking logic without touching the rest of the system. Now we have seen different parts of the search design already. Fuzzy search, ranking, and now there's one last piece we are adding, caching. So let's take a look at the final design diagram, which includes all the components working together to make Twitter search fast, accurate, and efficient. So here's how the system works, step by step. Step number 1. John types quantum computing into Twitter with a typo. So as soon as he hits search, his request is sent to the API gateway. API gateway is like the gatekeeper. It makes sure the request is valid and is ready to move forward. Step number 2. The API gateway forwards the request to the search service via the load balancer. The load balancer makes sure that the search goes to the least busy server, ensuring smooth and fast processing. Step number 3. Here's where caching speeds things up. Before hitting the database, the search service checks the cache to see if it already has keywords, quantum, and computing stored. Caching is like a fast lane for frequently accessed data. It's super quick. So unfortunately, the cache doesn't have quantum here. So what next? Time for the index database. Step number 4. The search service checks the index database but realizes there's no entry for quantum. So it calls query correction service to fix the typo. The service suggests the correct word quantum and sends it back to the search service. Step number 5. Now that we have the corrected keywords quantum and computing, the search service checks the cache again. If the cache doesn't have them, which it might not, the index database is searched. Once the index database returns the result, quantum appears in tweets 1001, 1002, 1003 and 1005, and computing appears in tweets 1002, 1003, 1005. Taking the intersection of both these results, the search service finally identifies the tweets 1002, 1003, 1005 as containing both the keywords. The system now updates the cache with these results, so future searches for these words will be faster. This is also called as read-through cache. So in using a read-through cache means that if the cache misses on a search, the search automatically updates the cache from the database. So future searches are very fast. Now in step number 6, Now that we have the tweet IDs, the search service checks the tweets database cache to quickly retrieve the tweet's content. If it's not in the cache, the tweets database is queried, and just like before, the cache is updated using the read-through mechanism. Now, step number 7, where ranking happens. So, with the tweets in hand, the search service sends them to the ranking service. The ranking service basically sorts these tweets based on the newest to oldest. By keeping this ranking logic separate from search process, we can easily change the ranking method later on. As we have seen in the previous one, we get decoupling via this way. And step number 8, finally the ranked tweets are sent back to John. He gets the most relevant tweets about quantum computing perfectly ranked from newest to oldest. So all of this happens in a matter of milliseconds. How amazing is that, right? Now, why this final design rocks? This final design is the perfect combination of speed, accuracy, and flexibility. By adding cache layers next to both index databases and tweets databases, we make sure that frequently accessed data is served lightning fast. With the query correction service fixing typos and ranking service ensuring the best results come first, John always gets the right results fast. And our system is flexible too. So that's it for the final design. That covers the whole search functionality where we have seen fuzzy search, caching, ranking, and indexing. Choosing the right database is like picking the right tool for the job. You wouldn't use a hammer to fix a watch, right? Similarly, the choice of database depends on the specific needs of your project. So here are some key guidelines for selecting a database. Number 1, fast data access. So when you need speed, NoSQL databases are often preferred because of their ability to quickly retrieve data, especially in systems handling massive amounts of requests. So imagine a Formula 1 car built for speed on specific tracks. NoSQL works very similarly, optimized for handling high velocity data access where milliseconds count. So it's super fast. So for NoSQL, you should think about using it when you need fast, flexible, and scalable access. It's designed to perform well in situations where large amounts of data are accessed very frequently. Now, talking about SQL, it is built more for structure and complexity. SQL shines when you need powerful tools to organize and manipulate data. So what's the intuition behind selecting a database? If your app has millions of users making simpler queries, like fetching a tweet by its ID, like in a TweetsDB, NoSQL excels because it's quick and direct. Second point, scaling up. Handling scale is one of the biggest reasons many large systems switch to NoSQL databases. Let's say your project starts small, but eventually grows bigger and bigger, like Twitter. It grew exponentially. So in SQL, handling millions of rows can become cumbersome as the data grows. So NoSQL databases, on the other hand, are designed to be distributed, meaning they can handle massive amounts of data by spreading it across multiple servers. So for NoSQL, if you're expecting scale, this is the go-to because it was built to grow. Systems like Google, Amazon rely on NoSQL for this reason for many of their use cases. Now, talking about SQL, while SQL databases can scale vertically, getting a bigger machine, that is what vertical scaling is, NoSQL scales horizontally, adding more servers as your data grows. So the intuition is, if you need to handle billions of tweets, like in our TweetsDB, NoSQL is the hero because it can grow alongside your data. Now our third point is data structure. If your data has a fixed structure, think of data like names, ages, or employee IDs. SQL is fantastic because it organizes data into tables and rows. It's like a library. Everything has a specific shelf and its place. But what happens when your data doesn't fit into a fixed structure? Say you want to store tweets where some tweets have images, some have videos, some have hashtags, some may not have these hashtags, some may not have these videos. That's where NoSQL shines because it allows for a flexible schema. Data can eventually evolve over time without breaking your system. That's when we use NoSQL. Intuition. If your data is dynamic and evolving, NoSQL is better fit. The fourth point, complex queries. If you need to run complex queries like joining multiple tables or running heavy analytics, SQL is your best friend. It's designed to handle relational kind of data and offer powerful querying tools that make complex data relationship easier to navigate. Now, NoSQL keeps things simple. It's perfect for systems where the queries are more straightforward, not complex, like retrieving a value based on a key. So intuition. For something like retrieving tweets by their ID, you don't need heavy relational querying. NoSQL is ideal for fast key to value lookups. We are looking based on a key for all of these databases. The fifth point, data flexibility. When data is dynamic, constantly changing its form or structure, you want a system that can grow with it. And NoSQL is naturally flexible. So you should go with that. So intuition, if your data is growing and evolving, now what do we mean by that? It's saying that our structure of tweets might evolve with new features, new parameters there. That is when we use NoSQL. Now, based on these guidelines, we can say why NoSQL is the perfect fit for TweetsDB and IndexedDB. The first point is scale. We are handling millions of queries daily. NoSQL's distributed nature makes it perfect for handling massive traffic. So that's the scale. Second is the speed. For fast retrieval of tweets and keyword-based searches, NoSQL ensures low latency performance. So in that case also, we'll go with NoSQL. Third one is simple query patterns. We are mainly doing key value lookups, where NoSQL is a natural fit. I mean, we can definitely do that in SQL databases as well, but NoSQL excels in that. Its performance is much better than the SQL. And the last one is flexibility. So as the structure of our tweets evolve with images, hashtags and other features, NoSQL makes it easy to adapt without reworking the entire system. Let's now move on to the data modeling part. So before we dive into specifics of how our data is stored, let's first talk about the intuition behind data modeling. So think of data modeling as designing the blueprint of a building. Without a solid blueprint, the structure would fall apart. Similarly, if we don't model our data correctly, the system will break under pressure when handling millions and millions of searches. We all know that our search system for Twitter involves storing millions and millions of tweets and running search queries on them. To make this efficient, we need to think about what data we are storing and how we'll query it. So when a user searches for something like quantum computing, the system needs to quickly retrieve the right tweets and return them as results. Now, how do we make this quick and efficient? By indexing the important fields like tweet ID and keyword. So let's break this discussion into two parts. First, we'll discuss about the data modeling of TweetsDB. Then we'll move on to the IndexedDB. So the TweetDB. TweetsDB is where all the tweet data lives. Think of this as a main vault where the full tweet content is stored. So here's its full schema. It consists of tweet ID. This is the unique identifier for each and every tweet. It's like a fingerprint. Every tweet has a different one. Next, it has text. This is the actual content of the tweet, what the user is trying to post there. The third one is user ID. This identifies the user. This is the ID of the user who posted the tweet. The fourth one is created at. This is the timestamp indicating when the tweet was posted. Pretty standard, like all of these are pretty standard. Now, in the previous discussion, we saw that we'll be going for NoSQL databases for our TweetsDB. Now, the most common query here for our TweetsDB is when we are trying to find a tweet by its tweet ID. This is a rather simple query. We are trying to retrieve the tweet by its tweet ID. Now, because it has that common query, we'll index according to it. So to make this query fast, we create an index on the tweet ID field. This sets a shortcut to quickly find the tweets by their ID. Next, let's move on to the IndexedDB. Let's discuss the schema or the data modeling. The IndexedDB is a place where we store the map of keywords like hashtags, search terms to tweet IDs, where those keywords appear. It's like a mapping of keywords to their tweet IDs. Schema for IndexedDB is very simple. It has two fields, keyword and tweet IDs. So keyword, this could be a word or hashtag used in tweets. For example, quantum or computing. And the second field is tweet IDs. That is a list of tweets which have quantum or computing in them. Now putting it all together, the tweets DB stores the full content of each tweet, and that allows us to quickly retrieve a tweet by its tweet ID. And similarly, index database stores a mapping of keywords to the tweet IDs, allowing us to quickly find which tweets contain certain keywords. Now together, these databases make our search super efficient. The tweets DB gives us the tweet content, and the index database makes sure we can quickly search through millions of tweets to find the right results in a matter of milliseconds. Hello everyone, so in today's video, let's try to deep dive into the query correction service in our search system. So until now, we have seen how the query correction service magically turns John's misspelled words into what he actually means. But how does all of that happen? So let's pull back the curtain and look into what is happening actually inside it. So let's say John is planning a trip and he's in a hurry. He quickly types FERY into the search bar. Now that's not exactly a word, FERY. The actual word is FERRY, that is ferry. But we can probably guess that as a person. But our system doesn't know it. That's where query correction service comes into the picture. So let's see what it does actually. Now imagine if the query correction service is trying to figure out which word John meant when he typed FERY. There could be multiple options. So let's explore all of those. Let's look at our first one, which is FERRY. Here, there is only one transformation that is needed to convert FERY to FERRY. We just need to add R there. So that way, with only one change, we converted FERY to FERRY. Just one step. Similarly, it could think of FARE as well. It could have a transformation where there are only two steps. First, we replace E with an A. That converts FERY to FARY. Then, we change the Y to E. That changes FARY to FARE, fair. So two steps, still a possibility, but not as close as ferry. Now let's move on to the third possibility, which is FAIR. Here, we have the transformation which includes three steps. The first step, which replaces E with A, converting FERY to FARY. Then we can have the second step as inserting I, which converts FARY to FAIRY. And the final step is to remove that Y, converting fairy to fair. So result, we have three steps, not as close as ferry, but still good. So what's the closest? From our detective work, we can see that ferry FERRY is the closest match to FERY. With just one simple change, we add another R there. The query correction service selects ferry FERRY because it has the fewest steps required to transform FERY into a real word. So if you ask me, that seems to be very intuitive. Let me tell you a very interesting fun fact about this closeness between words. So in technical terms, the number of changes between two words is called Levenshtein distance. Think of it as a measure of closeness. The fewer the changes, the closer the words are. So in our case, the words FERY and FERRY had a Levenshtein distance of 1 because we only needed one change, that is adding R. For our case where we had FERY and we changed it to FARE, fair, that had a Levenshtein distance of 2 because we needed two changes. Similarly, for converting FERY to FAIR, we saw a distance of 3 because we needed 3 changes. So that is why ferry FERRY was chosen as the winner, and because it has the shortest distance. Now, the query correction service that we have here uses this Levenshtein distance to find the best match for your typos. When John types FERY, it checks for possible words and calculates Levenshtein distance for each one of them. Then it picks a word with the minimum distance, which is usually the closest match. In John's case, it suggested 𝗹𝗃𝗺𝗃 because it was just one step away from 𝗹𝗃𝗺. With this, John gets the right results in the search even if he made some little typo here and there. Now just to note, Levenshtein distance is one of the approaches that is used to find the closest word. Levenshtein distance is not the only one out there. But coming back to our query correction service, the query correction service makes our experience a lot better because this makes searching easier and more forgiving. It doesn't rely on exact matches. It looks at similar options and picks the most likely one. So even if John types 𝗹𝗃𝗺𝗃 instead of 𝗹𝗃𝗺𝗃, he'll still get information he's looking for. That's the power of smart search technology. In this video, let's talk about Elasticsearch. Let's explore something interesting. The design we have built here, API gateway, query correction service, search service, ranking service, and index databases, actually mirrors a powerful real-world tool called as Elasticsearch. So what is Elasticsearch? Think of Elasticsearch as a supercharged search engine. It's designed to handle massive amounts of data and deliver real-time search results, real-time. It can perform complex functions like fuzzy search to handle typos, and it even ranks search results based on relevance, just like how we did it with our ranking service. In fact, if we replaced our design with Elasticsearch, it would work in very much the same way as Elasticsearch. Obviously, there are more complicated designs in Elasticsearch, but the overall gist or overall summary of the design is very similar. Our Elasticsearch can manage huge data loads while keeping the search fast. It can also handle typos with fuzzy search similar to our query correction service. And it can also rank our results based on relevance like our ranking service. Now, talking about real-world usage, Elasticsearch isn't just theoretical concept. It's widely used by tech giants like Twitter to manage vast amounts of data and deliver fast, accurate search results. By using Elasticsearch, Twitter ensures that users get the information they need, even with typos or complex queries. Elasticsearch offers a very powerful, scalable, and ready-to-meet solution that you can leverage in your projects, and even big companies and small companies are already using it.